Welcome to the video on the limits of sequences. You've spent a lot of time talking about sequences and series, but now we're actually going to take a look at some pretty interesting sequences. For example, we are looking at the limit as n goes to infinity of the sequence that would be defined by n minus 1000 over n minus 1. If you wanted to think about what that sequence has in as its terms, you could plug in a series of n values, right? And you could actually look at those terms. However, I think you actually know a lot more about that expression than you may have realized. That's a rational expression. And that means that when you graph it, it's going to have an n behavior asymptote. So you should know exactly where that EBA is just by looking at the degree of the numerator, comparing that to the degree of the denominator. So let's see. The degree of the numerator here would be 1. The degree of the denominator would also be 1. So we have an equal degree situation here. And when that occurs, you actually look at your leading coefficients. So 1 over 1 is 1. So we know that the answer to this problem is 1. Right? As I go out all the way towards the right, this as n goes to infinity, the graph is going to approach the EBA, which is at 1. So now, why was this a whole new video? Why are we calling this a new topic? Well, that wasn't really a new type of sequence, right? That's a rational function. You have some experience with that already. But what I do want to emphasize is this idea of a limit as n goes to infinity, and thinking about how you might determine that if you didn't know, for instance, what the EBA of this function was. Shouldn't you be able to think about n as being a really, really large number? Right? So if I plugged in a number for n here, considering it is really large, shouldn't I be able to know that the answer is 1? Well, there's an issue with that. What does it mean to be large in this situation? Is 10 large enough? Is 100 large enough? Is 1000 large enough? Right? Let's just take a look at what those values would produce. Let's say n equaled 10. That would mean that on the top we would get negative 990. On the bottom we'd get 9. So what's negative 990 divided by 9? Negative 110. That is nowhere close to what the answer is. But then again, you might not have said that 10 is a large number. Okay, I'll give that to you. What about 100? Is that large enough? Let's see what that gives us. Wouldn't that be negative 900 over 99? What's that? Negative 9.09 repeating? Again, that's nowhere close to this. That's a negative number. The answer is positive 1. 100, I mean, that's pretty large, right? Let's go another tenfold out. Let's go to 1000. Is that large enough? The numerator is going to be 0. I guess it doesn't even matter what the denominator is going to be, right? I'll write it down anyway, 999. That's 0. Okay, at least we're moving in the right direction here. But I hope you're getting the idea that plugging in a large number may not be the best course of action. You could, I guess, keep doing this, right? Keep getting bigger and bigger to see if you actually start to approach something. Let's go to 10,000. So that would give me, what's that? 9,000 over 9,999. Okay, this is looking better. What's that? 0.9, looks like 000 repeating. That's getting much closer to 1. Let's keep going. Let's go out to 100,000. 100,000 would give me 99,000 in the numerator. 99,999 in the denominator. That's about 0.99. Okay, that's really close to 1. And I think if we went out to 1,000,000, we would get 0.99 again, right? So we would, again, we're starting to approach it, but like, how do I know? Like, maybe I would have to go out to 1 trillion to get there. I mean, this isn't a great method. I guess, you would eventually would get there, but we want to try to avoid doing this. This is not a great way of doing it. It's almost like a guess and check method. We want to be able to look at this expression and see if we know something about it. Okay, so this was an example. We know that the EBA was 1, right? So I know that as n goes to infinity, this graph approaches that. Now let's look at an example that is not a rational function. That is absolutely not a rational function. Looks like we have an exponential in the numerator and a factorial in the denominator. Okay, that's just weird. So let's try to get a handle on the situation here. What are the terms of this sequence doing? Let's start with 1. If I plugged in 1 for n, I would get 5 over 1. So I get 5. But if I plug in 2, that means that this would get multiplied by 5 again, right? You'd have 5 squared. And what would happen down here? We'd have a 2 factorial, so then that would be a 2 times 1. Okay, so this is going to be 25 over 2. But then if I went to n is 3, then I'd have 3 of those 5s up there, and 3 factorial will be 1 times 2 times 3. Oh, I think I'm starting to see something here. The top is always going to remain 5s, right? And the bottom is going to grow, right? There's like this consistency to the top, and there's this growth happening in the bottom. So now look at this. If you were to just focus on the first fraction, the top is bigger than the bottom. Now look at both fractions here put together, the first 2. Still the top is bigger than the bottom. Obviously 5 times 5. You don't even have to know what 5 times 5 is. You know that 5 and 5 are bigger than 1 and 2. Let's think about that idea out to where the 5 is in the bottom. Look at this. These are now the same, but all the rest of these are bigger than these, right? Something changes, though, right here. Now the 6 is bigger than this 5. And if I were to go out to this idea of infinity, which is the limit is asking me to do, aren't these numbers that I'm writing down right now, aren't those always going to be bigger than the number I'm writing up here? So let's think of how this thing grows. The bottom is going to grow a whole lot faster than the top is going to grow. Now I did say it's consistent. I'm consistently writing 5s there, but it's still growing. 5 times 5, right, that's 25. Multiply that by 5, that's growth. Multiply by 5 again. But it's a very consistent type of growth. Here, I'm multiplying by a bigger number each time. So I'm going to describe this one as 5n grows, right? It definitely grows, but n factorial grows faster. That's how we should be looking at this one. And if the denominator is growing faster than the numerator, right? And I want to go all the way out here and look at what this giant multiplication problem would be. Wouldn't the bottom be so much bigger than the top that that would be the same thing as saying 0? Right? The bottom would be so big compared to the top. That's the same thing as saying 0. So this idea of growth, looking at the numerator compared to the denominator and thinking about growth. Let's use that to finish the next example. What's going on in the numerator versus the denominator here? The numerator, that's growth, right? That's just a bunch of 3s being multiplied. But look at the bottom. That's huge, right? What is that? 100,000 times x cubed. Oh, that's got to be pretty big, right? No, I think that might be a little trick there. Just because there's a big number in the denominator doesn't mean it's growing fast. Let's take a look. 3 to the x. That's a bunch of 3's being multiplied, right? That's not going to change. Well, what's happening in the denominator? There's only one of those 100,000s. That would get multiplied by what? If I had 4 of these 3's, that would mean that x is a 4 here. Oh, that would be multiplied by a 4 times 4 times 4. There'd only be 3 more numbers there, and that actual number is what's going to change, right? So if you had 4 of these 3's versus these 4 numbers, I guess that, this number is big enough where we'd say, oh, that goes to 0. But remember, we're going out here to infinity. I'm looking at a whole bunch of these 3's, right? Let's take an example. Let's say I went out to 1,000, right? 3 times 3 times 3 times 3 all the way, and there'd be 1,000 of these, 1,000 of these, over 100,000 times 1,000 times 1,000 times 1,000. Now, look at the bottom. I can actually do that pretty easily, can't I? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Isn't that a number with 14 zeros on it? Well, let me get them all here. Now think about this. 3 times 3 times 3, 1,000 times. What is that going to be? Our calculator can't even handle it. Let's make a smaller number. Let's see what it can handle. What if there were only 500 of them? It's still too big. Okay. What if there were just 100 of them? Look at that. That's right there. That's convincing me that this number is so huge compared to this one. Look, this is 5 times 10 to the 47th, and that's only when this number was 100. It really should be 1,000 to compare to this number, right? So what is this? It's so large, the calc doesn't know, right? So I'm going to write down my comparison here. 3 to the x grows much faster than 100,000 x cubed. An exponential, does that always grow faster than a cubic? Maybe. Maybe we should talk about that more in class. That's exactly what we're going to do. So now, in this case, we do know that this is growing faster than this. This number out by infinity, that's always going to be huge compared to this one. Well, when you take a huge number compared to a really small number and you divide them, right, don't you get a really huge number? Which is why the answer to this one is infinity. All right, so there's a nice sample of some sequences that were not arithmetic or geometric, but we know what they are going to approach anyway. We'll do some more in class. We'll see you then.